Hello and welcome to a review session of Math 225, Discrete Mathematics. Today we're going to be solving a sample paper with some questions to review the final exam. So, the first question says to use the definition of big theta to show that 4x cubed minus x squared minus 3x plus 5 is in big theta of x cubed. This essentially means that it's bounded above and below by different copies of x cubed, each of which is multiplied by some constant. So one of them is multiplied by a bigger constant that makes it always greater than this polynomial after some point. And the lower bound is also an x cubed multiplied by a constant that is small enough to make it always smaller than this polynomial after some point again on the x-axis. The exact definition of big theta tells us that if there are constants c1, c2, and x0 such that c1 times g of x is less than f of x and f of x is less than c2 times g of x for all x greater than this x0, then we say that f of x is in big theta of g of x. Essentially, like you could say, for example, that f of x is sandwiched between two different copies of g of x that are multiplied by two different constants. So the first part here, c1 g of x is less than or equal to f of x. This is the lower bound part, which is the big omega part. And the second part, f of x is less than or equal to c2 times g of x, is the big O part, which is the upper bound. So we can simply, instead of using the definition directly, we can use the definition of big O and big omega together. So the first part, to show that the polynomial is big O of x cubed, goes like this. We first write the polynomial, we say that it's less than or equal to some constant times x cubed, which is the function in here. Okay. Now, in general, when dealing with polynomials in these types of questions, it's best to take the highest degree term and check its coefficient, and let c be equal to any number greater than that. Okay, so anything greater than 4 would work. The simplest choice in this case would be 5, since 5 minus 4 is 1. So yeah, we write this inequality with c equal to 5. 4x cubed minus x squared minus 3x plus 5 is less than or equal to 5x cubed. We subtract 4x cubed from both sides to get x cubed greater than or equal to minus x squared minus 3x plus 5. Now we bring over the negative terms to the other side to get x cubed plus x squared plus 3x greater than or equal to 5. Now, this inequality, if we put it in the calculator, is going to be true for all x greater than or equal to 1. Know that I use the greater than here. So we can choose x0 to be just 1. Okay. Now we've proven that the polynomial is big O of x cubed, and now we have to prove that it is big omega of x cubed, which means it's bounded below by some constant times x cubed. This means that it's greater than this constant times x cubed for some for all x greater than x0. Now, again, instead of because with the big O, we chose a c that's greater than 4, but in this case we want a lower bound, so we can choose a c that's smaller than 4. So the easiest would be 3. So we put that into the inequality, substitute, we get 4x cubed minus x squared minus 3x plus 5 is greater than or equal to 3x cubed. And subtract 3x cubed from both sides, we get x cubed minus x squared minus 3x plus 5 greater than or 0. Now it's really nice that we have a 0 here. So we want to see where is this inequality always true? Past what x0? So in order to do that, we can just simply solve x cubed minus x squared minus 3x plus 5 equal to 0. And then we have that as our x0. So if we do this, to solve this in the calculator, we get minus 1.91964 something. And so after this number, for all x greater than this number, this inequality is going to be true. Therefore, the above inequality is going to be true. And because of that, since we have some constant and some x0 that make that have this inequality always true, the polynomial is big omega of x cubed. Now, in this case, according to this given definition from the slides that you were given, we have only one x0, but you can have two, it's fine. One for the big O part and one for the big omega part. It doesn't really matter. Although if we were going to choose one, we can just pick the bigger one of the two. So we had a 1 here and minus something here. Bigger one's 1, so that's our x0. And C2 is 5, C1 is 3. Next. Oops, why are these all open? Give a big O estimate of each function. So in the previous question we did a proper, more or less, proof that the function is big O of some other function. But now we just need to give an estimate, which is like simply look at the highest order term and say that the function is big O of that. Okay? So in this function we have n log base 2 of n plus n minus 1 all squared plus 2 to the n. Now the n minus 1 all squared becomes n squared minus 2n plus 1. So we have 5 terms essentially. N log base 2n, n squared minus 2n, 1, and 2 to the n. Now obviously 2 to the n grows way faster than all of these. So we can just say the function here is big O of 2 to the n. And since big O can be a loose or a tight bound, you can honestly choose anything that grows even faster than 2 to the n, and it will still be correct. But for accuracy's sake, it's more practical to choose the tightest fit in this case. Okay. Now, for this, it's easier to just check, since it's a multiplication of two different polynomials and carrying it out would be annoying. You want to just pick the highest order here and the highest order here, and you get n to the 7. So the function is big O of n to the 7. Now, next question is a word problem. You need to look at it carefully. So at the beginning of each day, Andrew adds 1 gallon of water to his bird bath. Each day, 1/3 of the water in the bird bath evaporates. At the end of day 0, the bird bath contains 8 gallons of water. This is our base case. So now name of the function is w. So give a recurrence relation for w of n, the amount of water in the bird bath at the end of day n. Okay. Now we said that the base case w of 0 is equal to 8. Okay. The recursive part goes like this. So Andrew first at the beginning of the day adds 1. So we had some number w of n minus 1, which is the previous day, the amount of water left after the previous day. We add 1 to that, and then during that day after Andrew added the water is gonna evaporate. So we have w of n minus 1, we add 1 to that, and then the sum is going to be multiplied by 2 over 3, because 1 over 3 of it is lost. So this is our recurrence relation. We have the previous days, and then we add 1 gallon, and then we multiply by 2 over 3. and the base case was w of 0 equal to 8. Next question. Suppose that you are collecting coins to make hexagons in a natural way by packing circles as tightly as possible. The figure shows how 19 circles fit into a hexagonal shape with 3 circles on each edge. Okay? So, this hexagon has 3 circles here, 3 circles here on each edge, 3, 3, 3. Now, the hexagon is composed of several equilateral triangles, and each of those has an edge length of 2 circles. Okay, so the recurrence relation we want is for the number of circles in each single triangle. Okay, so for a triangle of with 2 circles along its edges, it's gonna have 3 circles in it, and then if we try to imagine a circle with a greater number of a triangle with a greater number of circles, the next triangle we can form is going to look like 1, 2, 3, and then 4 here, 5 here, and a 6 here, and that's going to give us t of 3 equal to 6 according to the question. Now the next triangle is going to have 4 more circles. So we had 1 here, 1 here, 1 here. I can't really draw on this, so just bear with me. The next ones are going to be here, 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 and here. So we had 1 over here, and then 2 here, then 3 on the next row, and 4 on the following row. So we had 1 plus 2 plus 3 plus 4. Although in this case it's usually easier to take the base case to be 2, edge length 2, because 1 circle isn't really a triangle. So anyways, we have the base case equal to 3, t of 2 equal to 3, and then we have t of 3 equal to 6 because 3 plus 2 plus 1 equals 6. And then t of 4 is going to be 10 because 1 plus 2 plus 3 plus 4 is equal to 10. And so we started at 2. To get to t of 3, we added 3. To get to t of 4, we added 4. So essentially each t of n is equal to n plus the previous number. Okay, so t of 3 was 3 plus t of 2. T of 2 was 2 plus t of 1, which is 1, although t of 1 isn't really defined the way I solve this. So yeah, t of n is equal to t of n minus 1 plus n for all n greater than or equal to 3. And I should have added extra that t of 2 is equal to 3 for the base case. Okay, now putting this into the other app would have been too much effort, so I didn't bother. Excuse the flashbang of going from dark mode to light mode. So, question 5 gives us a recursive binary search algorithm which tells you whether a given number is in some list of numbers, or an array, you can say. Okay. An example given to you in the question is that suppose you have this list of numbers, the multiples of 3 between 3 and 30, and you want to find 21. Now it's good to represent these as indices. So this is x1, this is x2, this is x3, so third number, fourth number, up to the 10th number. Okay, so 21 would be the 7th number in this case. Now binary search essentially, it assumes that the array is sorted, and then it's gonna look in the middle part of the array. In this case, it's gonna look at 15, and it's gonna say, is 15 greater than or less than 21 if it's not equal. And since 21 is greater than 15, it's gonna remove the entire left half of the array and focus its search on here. And then it's gonna compare against 24 and it will see that 21 is less than 24, so it's gonna check only indices 6 and 7. And then it's gonna compare against 18, finds that no, this is not the 21 is in the right side of this subarray, and then it's gonna look here again, focus here, and it will see that yes, this number is in fact in the array, so it returns 2. Now we're going to follow the steps more precisely when solving the actual question. Now, the question says evaluate binary search of 3, so we want to find 3, x, this given the same set given to us, 1, which means the first index, and 10, which is the last index. Now the reason we're given the indices here is because this is a recursive algorithm, so it's going to be calling itself but with different indices to determine like which half of the array is going to be searching in. So let I be equal to L plus R divided by 2 float. So L is our 1, R is our 10, 1 plus 10 is 11, divided by 2, that's 5.5, and then the floor is the greatest integer that is smaller than 5.5, so we have 5. So I is equal to 5. Now, if t, which is 3, is equal to x of I, so the fifth number, in this case 15, then return true. This isn't the case, so we're not going to bother. We're going to check the else part. The else part says if t is less than x of I, so if 3 is less than 15, and 1 is less than 5, which is also true, then we return binary search of 3, x, 1, and 4. Okay, so we're gonna check this part, 3, 6, 9, 12, and we're going to start over again. I is equal to L is 1 plus R, which is 4, divided by 2, so 1 plus 4 divided by 2 is equal to 2.5. Store that, we get 2, so I is equal to 2. Now if t is equal to x of 2, then return 2. X of 2 is 6, 3 is not equal to 6, so we don't do that, we go to the else part. If 3 is less than 6 and 1 is less than 2, then return binary search of 3, x, 1, and 2 minus 1 equals 1. Okay, so now we're going to focus our search on just this subarray, and obviously it's right there. So let's go again. I is equal to L plus R, 1 plus 1 divided by 2. So this is just 1. Now if 3 is equal to x of 1, now x of 1 is the first element, which is 3. 3 is equal to 3, so we return true. And that concludes part A of the question. And I gave you explicitly all the steps. If we were going to write this as an exam, then do that. Okay, now part B of the question states find the recurrence relation of the number of comparisons t equals x of I, t greater than x of I, and t less than x of I as a function of the form c of n, where n is the size of the input data. So the base case of this is if the array is of size 1, okay, and in such a case you can make one comparison in case your search key is equal to that number. So if you're searching, let's say 3x11, you're going to be looking for 3 inside of x with left and right equal to 1, so you're going to make only a single comparison. Or if your search key, let's say it's 2 instead, it's going to be less than the the element of the array, a single element of the array, then you're going to be making up to 2 comparisons. Or if it were 4, let's say, so you're searching for 4x11 for some reason. Then you're gonna have the third comparison. So you're gonna have t is equal to x of y, t is less than x of y, and t is greater than x of y. Okay? So you can have up to 3 comparisons. And you don't know which one. It could be anything. Now, you can actually abstract this a little and just say that the number of comparisons is k, okay? And then, the other thing you need to notice is that binary search cuts the array in half every time you make a comparison. Like every time it finishes with those 1 or 2 or 3 comparisons, okay? And after cutting it in half, it's gonna run again on the array of half that size. So the running time, let's say t of n, is gonna be the running time of t of n over 2, which is the running time on half of the array, plus the time you need to make these comparisons, okay? So we have the recurrence relation t of n equals to t of n over 2 plus a constant k. Okay, now part C of the question says find the closed form solution of the recurrence relation c of n obtained in part B and use it to approximate the worst case complexity of the recursive binary search function as big theta. Now, intuitively, we already know actually that the worst case complexity is big theta of log of n, because notice that the array size gets halved every time. So if we had 10 elements, it's not going to be 5, then 2, then 1, and done. So having doubling the array size, let's say we had 20, it's going to get halved to 10, and then we're going to have the 3 more halvings that were done to the array of size 10. Okay, so doubling it only increased it by 1. That's characteristic of the log of n complexity. Now, let's switch over to the other part, dark mode. Okay, so I've written the question here again. Find a closed form solution for the recurrence which we found in part B, and that was t of n equal to t of n over 2 plus k. Okay, k again represents the number of comparisons done in a single function call. K is can be 1, 2, or 3. We can cap it at 3 if we'd like as the worst case complexity, so we can say like that, although it doesn't really matter. You can say 3, you can say k, you can say O of 1 even, if you so desire. So the t of n over 2, according to this rule, is going to be t of n over 4 plus k. So we can substitute t of n over 2 with that to get t of n over 4 plus k plus the previous k that we had to get 2k. And then we do that again. T of n divided by 8. So we divided that by 2, and then we added 1 to the k. We divide by 2, add 1 to the k, and so on and so on. And so we can actually represent this as a more general way as t of n divided by 2 to the m plus m times k. So we have it by 1 every time, and we add this by 1. Increment this by 1 every time, okay? And we need the base case as well, which is an array of size 1 having up to k comparisons, up to 3 comparisons, let's say, okay? Now, clearly, eventually t of n by 2 to the m is going to reach 1, okay? And so we set n over 2 to the m to be equal to 1 and solve for m. We're going to get m equal to log base 2 of n, okay? And so we can represent the recurrence relation as n equal to t of 1, okay, plus yeah, mk, okay. So t of n equals to t of 1 plus mk, and m, like we said before, is simply log base 2 of m. So the t of 1, we're going to substitute it with k, and the mk is going to be substituted with its actual value. So log base 2 of n multiplied by k, right? So we have the k from the t of 1 and the k log base 2 of n from the mk, or kn if you'd like. And so we have a constant and a constant times log base 2 of n. And the higher order term of these two is obviously the log base 2 part, and that gives us that this function is theta of log base 2 of n. That's the solution for part C of question 5. Moving on to question 6. It says to define a set X of strings in the symbols 0 and 1 as follows. 0, 1 and 1, 0 are an X, and if X and Y are an X, then so is XY. Now, what is a string in the symbols 0 and 1? You haven't really taken this in your studies, but it's fine. It's like just a few extra definitions you need to keep in mind. Now, symbols are basically like characters, like in the C language. If you wanted to make a string, you could go char my string, an array like H, E, L, L, and O. Okay? Technically, you'd also need to follow it up with a with a null character, but that's not our concern here. So here H, capital H is a symbol, E is a symbol, lowercase l is a symbol, and O is also a symbol. Okay. Now a string in the symbols 0 and 1 means a string much like that, much like this one here, that is composed only of zeros and ones. Okay. Now the base case is that you have two strings in X, 0, 1, so 0 followed by a 1, and 1, 0, which is a 1 followed by 0. Don't confuse these with the actual numbers 1 and 10. These are very different things. Okay? Now, if X and Y are in this set, and so is XY. So we started with these two, and we're going to add more elements to the set according to the recursive step. So, part A of the question says, explain why 0, 1, 0, 1, 1, 0 is an X using the definition. So this was our definition, and we're going to use it to explain why this number is in the set. Build up the string step by step and justify each step by referring to the appropriate part of the definition. Okay, so let's check the solution here. We can let, okay, now we need to discuss also what xy means, and we'll do that as we go. So let x equals 0, 1 and y equals 0, 1. Okay, this is true because both of them, both 0, 1 and 0, 1 again, are an x. Okay, xy, this looks like a multiplication, but when you're dealing with strings, this is actually a concatenation, which means put all the symbols in x, put all the symbols in x, and follow them up by all the symbols in y. So x had 0, 1, so you're gonna take 0, 1, and then you're gonna take the characters in y, which are also 0, 1. So xy is gonna be 0, 1, 0, 1. So this is the x part here, and this is the y part here. Okay, now we continue. We let x be the same string that we just constructed, xy equals 0, 1, 0, 1. We let that be x, and we let y be equal to 1, 0. Again, both of them are an x. Y equals 10, 1, 0. Even I made that mistake. Y equals 1, 0 because of the definition saying that 1, 0 is an x, and 0, 1, 0, 1 is an x because we just showed that. Therefore, the concatenation of x and y here, which is 0, 1, 0, 1, here, 0, 1, 0, 1, 1, 0, is also an x. That's done. Now, the second part of the question says, find a string in the symbols 0 and 1 that has the same number of zeros and ones, but is not in x. Okay. Now, you can pretty much just make a guess, like 1100 is going to be a counterexample that is not in the set, but we can do that. We can find the solution more systematically, and in that way we can also be sure 100% that it's correct. So first, you notice that we have the base elements of x have exactly 2 characters always, so 0, 1 and 1, 0, and then the other elements are all concatenations of those elements. Okay, so you'd always have an even number of characters in an element of x, and also because 0, 1 has exactly 1, 0 and 1, 1, and 1, 0 also has exactly 1, 0 and 1, 1, the result is that you're always going to have the same number of zeros and ones in a certain string. Okay, so when building up a string like we did in part 1, part A, we're doing that 2 characters at a time, and each of those two characters, each of those steps is either a 0, 1 or a 1, 0. Okay, so for example, this very long string, it was built by taking 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0. Okay, and yeah, each piece of here has exactly 1, 0 and 1, 1. And so with every single one you add, the number of zeros and the number of ones stays equal. This means that the strings will always have the same number of ones and zeros. This is a property of all the strings in x, and we need to find a string that has the same property, that it has the same number of zeros and ones, but it's not an x. And the way to do that is to check what pieces can we have that are different from these. So we had 0, 1 and 1, 0, but we could also have 1, 1 as a piece, or 0, 0 as a piece. If a string contains that, if it contains 1, 1, like as a single piece rather than like between 2 pieces, like notice here we have 1, 1 technically, 1 followed by another 1, but it's not a single piece. It's just like in the middle of the concatenation of 2 pieces. Okay, so out of all these 2 by 2 by 2 by 2 pieces, there's no 1, 1s and there's no 0, 0s. So a string that is not in x is gonna have necessarily as part of its pieces, 2 by 2 pieces, 1, 1 or a 0, 0. Okay, now the other thing is that we need to keep the same number of zeros and ones in that string, which means since 1, 1 adds 2 to the number of ones, we need to have a 0, 0 to counterbalance that number of ones, to keep things equal between the two. Okay, And so we need an equal number of 1s and 0s in our string. So one example would be 1100. This is not an x for sure, because the pieces are not 0, 1 or 1, 0. Another example can mix all of them together. You can have 1, 0 from x, and then 0, 0 not an x. And this is going to prove that, this is going to show you that this entire string is not in x. A more interesting example would be the empty string, which technically has the same number of 0s and 1s, which is 0 zeros and 1s, and technically is in fact in the symbol 0 and 1, even if it doesn't contain any occurrences of them. So there you have it, the possible answers to part B of this question, and that more or less concludes our review of Math 225, or our solution to the sample. So yeah, that's the algorithms and the the recurrence relations part of the course. For logic, you can take a look at the exam 2 sample, I believe. Should have a solution for it. Review that, check the slides if you need, focus on the definitions, how you can work out the examples using those definitions. Always the definitions are the most important part of this course. And yeah, that's it. Thank you.